Hi there. This is EE533's final project progress demo video demonstration. Uh, Today, this video is about single core multi-thread RISC-V based net processor, and in here we'll be covering a few highlights which are needed for this demo video one. The first one is our 4 threads capable of running independent tasks, but we have already demonstrated this in Lab 11's video, and I'll drop a link of that video here. But we have already demonstrated that all the 4 threads of our single core processor can run independent tasks, and uh, how we demonstrated that was like out of the 4 threads, thread 0 was acting as a parent thread, and the thread 1, 2, 3 were like child threads. Thread 0's job was to check whether it was a valid packet. By that we mean whether it is a UDP packet, so that other threads would be able to work on it. What thread 1 was doing was making the checksum of our IP datagram to be 0. Then thread 2 was making the checksum of the UDP headers 0, forcing 0 to be precise, and then the thread 3 finally manipulating and changing the payload's message. So earlier we were the client was sending hello Mumbai, and actually due to the thread 3's instructions what we wrote, we were getting hello Agarsa. The second thing is our FIFO, our data memory, working with the processor with the with polling feature, and we have introduced polling in our RISC-V processor from like lab 9 or 10, so it's been working just fine. And yeah, and in this video we have integrated the Hardware Accelerator mini-IDS with the processor, and I'll be demonstrating how it is working. So let's get on to the Verilog code. So in the IDSP we have instantiated the detect7b module. Within the detect7b module, it uses reg9b, word match, bus merge, all these things which we made using Xilinx IC's schematic based design. So in here you can see there are a few signals. So for the detect7b, basically the mini IDS, the chip enable, the signal is, the input is matcher chip enable, and this, let's trace the signal. So this is a wire, and the logic for this is when the fall through small fiber is not empty and the output is ready, that means the downstream wants the data. We enable the matcher, the IDS's chip enable, so matcher chip enable is high. Let's go back. Then comes the match enable. So in here this is signal info FIFO write messenger next. So this is basically the signal. Let's trace this down. So this will be found in our state machine right here. So this signal basically says that this is a valid packet, and this is the logic behind it. So when the fall through small fiber is not empty and the output is ready, and the controls, the 8-bit control signals are non-zero, that's when we make the signal high so that the processor can start working with the packet. Let's go back to the DETERLab module. Yeah, then there's a clock, and then the input for the mini IDS is the 72 bits. So like in-FIFO control and in-FIFO control, the in-FIFO data, and this is the output of our fall through small FIFO. So let me go through. So as we can see, the fall through small FIFO, the data out is the FIFO control, the 8-bit signal, and the FIFO data, 64-bit signal. Let's go back. Yeah, and this is the input pattern which we have given to the hardware register, and then we have the matcher mask signal. Before that, let's see what pattern we are trying to detect. So I'm going to just real quick translate this to ASCII. So I mean, basically the FF is like our mask here, but the pattern here is oh my Z shell, oh my Z SH. So this is the pattern we'll be looking out for, and if we detect this pattern, the matcher mask signal will be high, and the CPU, our processor, will do something about it. We'll go over that in the assembly code which I'll be discussing. So about this matcher mask signal, so we made this as the input to the processor because there needs to be some interfacing, because when IDS has done its job parallelly, it has to let the CPU know so that the CPU can do the real job, because in here we don't have a drop FIFO for the mini-IDS, so the processor needs to do the needful if there's an intrusion, and if there's intrusion, the matcher mask signal will be high. And yeah, match reset. So match reset is when our state goes to read ready. So in here, this is the logic. So reset, and like when we hit the reset for our whole system, or when the state goes to read ready. So in our state machine, which I discussed in the previous video, but I'll go through it again. Let this load. So this is our state machine, which is helping us interface the native agent processor interface the data memory. So start, this is encoded as 0, payload is encoded as 1, CPU is encoded as state 3, and read ready as state 2. So when there's a job complete and it is in read ready state, our mini-IDS will reset. So let's go through the assembly program. So it's kind of we have kept it a bit simple. So yeah, so first we are loading from the 256 virtual memory location. Here the FSM state is stored, and so we are loading this to the register RA, and then we're loading 3 in the register SP. Why 3? Because 3 depicts that the state is in CPU process, and that's when the processor needs to kick in and execute an instruction. And then we're executing a branch less than instruction. If it's not less than, so like if it's in read another state other than CPU process, it needs to go and again do the polling. If the branch condition fails, when it is in CPU process, so we'll go check the matcher signal. So parallelly, the IDS has done processing, and it would have detected, I mean, it would have given the output, which is matcher mask signal, to the processor, and we have stored the signal in this virtual memory location 2048. So we're loading this to the register GB, and then we're loading another value 1 in the in register TP, and then we're checking so branch equal. If it's 1, I mean, obviously, so like if the matcher signal is 1 and it is equal to the value stored in register TP, which we already load immediate as 1, it will go and do the steps in the destroy packet logic. If it's not, then it'll let the let FSM know, and it's job complete. So job complete is we have another virtual memory location 1024 address, where whenever we're done processing, we need to deposit a 1. So this is what it's doing. But if the matcher mask signal is 1, we go and destroy the packet. So let's see how the thread 0 destroys the packet. So in the virtual memory location 512, the read pointer is actually stored. So it'll go load, and then in all the 5 offsets, we'll just deposit store double 0000 everywhere, and then let the FSM know that it's a job complete. how we're letting that this job is complete by depositing a 1 in the 1024 virtual memory location, right? This is how a bit elaborate version looks like. You know, if it destroy packet, do all those things, and then jump -10 steps. As for the other threads, we have introduced knobs here for simplicity because in the previous video itself in lab 11 we have demonstrated that all our threads are capable of doing independent tasks. So right here, to keep things simple, we just made the other threads do no operations, knobs. So this is it, how it goes. So let me go to, yeah, and before generating the before generating the binary for assembly, yeah, so before generating the binary for the assembly, we need to give the start addresses for all the threads. So here I have given 12, 19, 20. Why? It's because we can see right, so we can see like thread 0's instructions start from 0, PC 0, then thread 1's instructions start from 12, so that's why I've given them. Then it should come 19, so here it is, and then 20. So this is why. Then we go ahead and generate the bit file. Already done that actually, right here. So this is how is the supposed working. Now let's go. So what we are basically doing is making we're using socket programming as we did before in lab 11. So we're making node 0 as a client and node 1 as a server. So node 0 will be sending messages, and then node 1 will be receiving it. So we're just initially setting it up as so we've done the socket programming using Python, so we're just setting it up. Let me go ahead and skip a little. Suppose sudo kill all. So here we are just downloading the bit file onto the NetFPGA. Now let's check if the ping works, and it does work fine. So here we're running a logic thief. So first it's a reset, and then it's kind of gimmicky sometimes, so I'll try it again. Ping is working fine. Again, loading the Python scripts. So in here, what right now we are doing is we loaded our let me show you. Yep. So this is a benign UDP Python script. So right now we are trying to send data to node 1, a server. This is a port, this is the IP for it, and the message here is hello world, and it should actually go through. So let's check it out. So yeah, as you can see, it went through. Now we'll go ahead and give the message where the pattern is actually present. So it's this thing. As you can see in the verilog file, when I converted that hex to ASCII, the text was "Oh my Z shell." So this should, if our system works, this should not display the message onto the server, and the processor should, you know, kill like force the packet to 0, right? So let's check it out. So as I run the script, see, I don't get anything onto the server, right? So let's check the log files generated from our logic thief, our logic analyzer. First, I'll check the benign payload. Let me close these. And let us just compare. So this was the benign payload. So the first 64-bit is the NetFPGA header, right? Here it is. And then comes a Ethernet frame, 14 bytes. So the first 6 bytes are my destination max. So 1, 2, 3, 4, 5, and 6, right? And then the remaining 4, and then these 4 makes up 6. The source MAC type 2, type our service type is like 2 bytes. Let me pick the 2 bytes here, right? Then comes the IP datagram. So it's IPv4, so that's why I just write it down. 4-bit 5, Helen length is 5, right? And service type is 00. The length is like this. So I've gone ahead and fill out the rest of the things of the packet. So all the sections of the IP datagram, the structures, and the EDB segment, and our payload, which is hello world. Let's check out the log for the malicious payload, because that's the one which would be interesting, whether the pattern which we did send, the malicious one, you know, would be dropped by our processor or not. I mean, not exactly dropped, but you know, forced to 0 and then sent to the downstream, right? Yeah, so actually in here, the thread ID, this has been mapped to, at the moment in our script, the match and match signal. So the one says the match and match signal is high, and you can see the state goes to 3. State 3 is CPU process state. So in here actually we should focus on the state 2, where the CPU is done issuing, I mean, all the instructions have been issued, and it should make force all the things to 0 for that particular packet. So in here if you see right here, it has, you know, store double 0 in all the 5 offsets. So we have all the 64-bit data. It's all 0 0 1 2 3 4 5. So this just demonstrate that our hardware accelerator, the mini-IDS, is successfully working with our single core multi-threaded RISC-V processor. And I think we have covered all the stuff, and at the moment we are still working on the dual core, and we'll have the demo 2 video out soon. Thank you.